All right, Calc BC, welcome to day 2. Thank you all for your input yesterday on the exit ticket, as well as 100% exit ticket turn-in. That is excellent for the very first day of this online learning. I'm excited to do another day with you with this online learning, and appreciate any feedback or ideas you can give me via email or through Google Classroom. Let's get started. So we're continuing our journey towards our big goal here. 30 out of 30 students will score 4 or 5 on the AP Calculus BC test on May 5th, 2020 to earn college credit in Calculus 1 and 2 at your respective institutions. Still shooting for that. I'm just going to remind us of that every single day because it'd be hard to remember that while we're at home before we head back to school. With that, I'm changing up the agenda a little bit based off some feedback. I'm going to do a quick exit ticket review during this video, follow up to exit ticket questions that you submitted, and then also cover the new content for today. Then during the Zoom call, I want to introduce a little bit more structure so we can get more done. During the first 10 minutes, I'm going to have a few check for understanding questions and time to take questions on the examples that you will see shortly. After that, we'll dedicate 20 minutes to independent practice support. That'll just be time where you're working, and I will look for the hand raises in Zoom to see who might have a quick question. I can also take quick questions during the chat, but stay tuned till then when we get there. And then I do want to leave you some time to start the exit ticket at the very least. I'm going to try to keep that in Google Forms because that allows me to gather questions from you really easily so I can follow up with those the next day. And as you watch this video, I would appreciate any feedback you have to make these even better for you. Trying a few different things, hope you appreciate it. So yesterday's exit ticket, we had 23 people choose A correctly, which is the correct answer. And so nice job with that. We had one person choose answer choice B, and then 6 people choose diverging. On the next slide, I've used PowerPoint transitions to walk us through the solution to this, as well as how to break down this prompt. I totally recognize this prompt is different than the ones we saw in class in the delivery of content, but you'll see it is actually very similar to the same process. Also, a quick note, I did give everyone a 10 out of 10 on this first exit ticket since I know it's your first attempt at this online learning. So even if you chose B or E, I still give you a 10 out of 10 for this assignment. Future exit tickets, you should expect to be graded based off your mastery. So when I read this prompt, first thing I'm going to think about is it's asking me for the area of R. And I know that I can find area from unit 6 using integrals. So then what am I finding the area between? Well, I know I have this function, y equals e to the negative 2x. So I'm going to look for the area between that curve and the x-axis, as it mentions in the prompt. And then there's this part that says x greater than or equal to 3. So greater than or equal to 3. So I know the lower bound for the integral is going to be 3, but what's the upper bound going to be? This connects directly to what we learned yesterday. The upper limit is going to be infinity. So from there, we get the integral from 3 to infinity. That's an improper integral, as we named yesterday. From there, we can convert this into our limit notation with limit as t approaches infinity from 3 to t, e to the negative 2x dx. Applying our antiderivative, we get negative 1 over 2 e to the negative 2x, evaluated from 3 to t. We can then break that apart, applying our upper and lower limits, subtracting. And from there, the limit of the first term, which is the only term with the t, if I think about that graphically, as t goes to infinity, e to the negative 2t is going to approach 0. And then the next term, there is no t, so we just take that value for what it is. And with that, the answer is A. Happy to take more questions offline on that when we're not in the Zoom chat, just so we can focus on today's lesson. I do want to recognize a few questions that people asked. Noah asked, I think we need more review or just more practice. Totally agree. We'll try to get more practice in during today's session, and then also find ways to support you throughout the day if you need additional support. Sade had a question. Can you upload the work needed to arrive to the classwork answers after 4 p.m.? I'm going to try to leave the correct answers in blue on the prompts from the problem sets. And then what I can do today is upload that after I've had a chance to review people's work. I'm a little hesitant to just upload the answers at 4 because I don't want people to be tempted to just copy down my answer key. So I'm giving you the correct answers just so you have that for reference, and we can adjust this as needed. Carla had a question. Do we need to evaluate an integral if the integral diverges? Just like series, if it diverges, you can't find a value for a series. For an integral, if this integral diverges, you can't find a value for the integral. So you don't need to find its value. Paul's question was, I don't really have a question on this lesson, but I forgot when to use u sub, the antiderivative, etc. Great question, Paul, and really good point. So today I'm going to remove all u sub, integration by parts, all the complexity of antiderivatives, and just focus on the improper integral component where we're dealing with infinity. Then Nathan had one quick question on yesterday's lesson. How do you solve when both limits are approaching infinity and negative infinity? Great question. Look at example 3 in the 11:18 video. And then a quick verbal summary of that, Nathan, is you need to break the integral up into separate integrals with a common middle point. Then evaluate each integral separately. And with that, we're going to jump into 11:19, improper integrals part 2. I have a few recall slides in here just to connect to your prior knowledge, so stay tuned for those in a moment. And I hope this helps you see how everything really connects. Recall, we looked at an integral on the left, like one on the left, from 1 to infinity of 5 over x squared dx. And this involves a definite integral with an infinity in the upper limit, lower limit, or both. That's what we saw yesterday. Today, we're going to analyze another type of improper integral. This one doesn't look up improper initially, as the limits are not infinity, but we're going to see soon that it is actually improper for a very similar but slightly different reason. So a couple quick recall slides just to make sure we really got the foundational knowledge down. In Unit 6, we covered definite integrals. Remember, definite integrals represent the area underneath the curve from some lower limit to some upper limit. In this case, I have the integral from 1 to 4 of 5 over x to the 4th dx. And I have a graphical representation of this on the right. And so we have finite values in the upper lower limits. The area is clearly finite, as we see. And when solving, we see this integral would be equal to 3.75. You can do that by hand or using Math 9 in your calculator. But we know how to do that, just a quick recall. And so finding that integral tells you the area underneath the curve in green. So again, if the area is really clear and finite, antiderivative, upper lower limits substituted, and subtract will get you the area. Another recall slide back to yesterday. This was the same integral we saw 2 slides ago. You'll notice it's immediately an improper integral due to that infinity in the upper limit there. And so this area continues infinitely to the right. So I'm going to annotate that real quick. This just keeps going to the right. It doesn't stop here at, say, 7 or 7.5. It keeps going to the right because of that infinity symbol up here. And so if we use our process from yesterday, we would find that this integral actually converges to 5. For this next part, I'm going to show a quick thing on Desmos, because I think this does a great job of demonstrating the next point. Just a moment, turn off my annotations. Okay, so this is the integral we're going to look at. Whoops, sorry, too far. This is the integral we're going to look at, where we have an integral from 2 to 6 of 1 over square root of x minus 2. So if I flip over to Desmos, here we go. Hopefully you can see my Desmos screen now. Double check that. I'm going to stop my share and switch over to Desmos. Great, now you should be able to see this. So if we have this integral here, and if I try to plug in 2 for my integral, we get this number really close to the answer of 4. So let's find out what's going on here. We have 6 over here as my upper limit, and that's why we see the area stops over here at the right. But then as we approach 2, we're seeing something interesting happen with the curve. We have a vertical asymptote here at x equals 2. Get a different color. Annotate, format, let's use red. There we go. So we have a vertical asymptote here. So instead of the area going infinitely to the right, the area is actually growing infinitely as we move towards 2. So If we flip back to I'm going to stop my share, flip back over to our PowerPoint, we have a vertical share. There we go. We have a vertical asymptote at x equals 2. And so that area is going to continue upward unbounded. And the area continues infinitely as we approach 2 from the right. So as we approach, let me get my annotation tool back out. As we approach 2 from the right, this area, although it keeps growing as we get more and more area up in this area and we keep going, it's going to converge to 4. So we're going to see how that math works out momentarily. It does converge to 4. So that's the second type of improper integral where it happens at a vertical asymptote. Whereas, let me clear all my drawings. Whereas if we look at the previous slide, this had an integral, the area growing infinitely to the right. So with that, let's do a quick check for understanding. Pause the video and consider these 3 questions on the left. Great, so you should have an idea of which ones you think are definite improper integrals of the first type from yesterday or improper integrals of the second type from today. Let's see what the answers are. So integrals b and d are both definite integrals. One way we can quickly see that is that the upper and lower limits are finite. And then if I think about if there's any discontinuities, I know that 1 over x cubed is only discontinuous at 0. It is not discontinuous between 1 and 6. So b is a definite integral. Same thing applies for d. X squared is never discontinuous. It's always continuous if you think about your parabola. And so that's another definite integral. If we look for one that looks familiar to yesterday, we see the integral from 1 to infinity, 1 over x cubed dx. That is an improper integral of type 1, like we learned yesterday. Then let's think about why integral c would be an improper integral as well. Well, if I think about the curve 1 over x cubed, there's a vertical asymptote at x equals 3. Or sorry, x equals 0. It's that left endpoint of the integral, that lower limit of 0. There's going to be a vertical asymptote there, making this an improper integral like the ones we see today, or I like to call them type 2. With that, I'm going to switch over to the doc cam to do another example. We're going to have 3 examples today, and I'll see you over there in a second. Here we go. Example 1. So removed all U substitution, complicated methods of integration. I'm just going to focus on how to handle this question. So evaluate the following integral. This doesn't look improper initially, but if I think about if I plug in 2 here, 2 would make the denominator 0, which would make this whole fraction undefined. And so I'm going to make a quick annotation. There's a vertical asymptote at x equals 2. And that's going to tell me that this is a improper integral. So with that, we're going to have to apply some similar principles to what we did yesterday to this case. Let's start with this integral, and I know that this is going to be the location of a vertical asymptote. So what I can do is rewrite this integral with a limit as t approaches, and I'm going to approach 2 from the right. Remember that plus sign of the exponent area there? That means from the right. I'm going to rewrite the integral, replacing that lower limit, and then keeping the upper limit and writing the rest of the integrand. And I'm going to call that rewrite with limit definition. Then from there, I'm going to apply my same antiderivative plug in upper lower principles here, and then we'll handle this limit at the end. So I rewrite my limit. And when I think about the antiderivative of this, the antiderivative of that is going to be 2 square root of x minus 2. Derivative of my inside function is 1, so I don't need to worry about anti-chain rule here. And this is evaluated from t to 6. So this was antiderivative. Then from there, I'm going to substitute my limits. I'm going to keep t approaching 2 from the right, and I get 2 square root of 6 minus 2. minus 2 square root of t minus 2. I'm taking the limit of this whole thing. And so that was sub limits. Then from there, I need to just evaluate my limit. This first part, square root of 6 minus 2, there's no t in here. So it's just going to be a constant, which is square root of 4 times 2. So that's 2 times 2. I'm going to write that's equal to 4. Let's take a look at this second part. I'm taking the limit as we approach 2 from the right. So if I think about this function graphically real quick, this would look like this. And if I approach 2 from the right, at t equals 2 here, that's going to approach 0. So I'm subtracting 0, and this ends up being just 4. We switch back to the PowerPoint. Stop my share, switch back to the PowerPoint. Here we go. We saw back here in the new content slide that approached 4, and what we just did on paper is prove that integral equaled 4. So we did it algebraically. We saw it graphically in Desmos, but we just proved it algebraically. We need to pause and rewind. Go for it. We're going to move to example 2 now. Here's example 2. And before I move back to the DotCam, notice how it's the same limits of integration, but I have changed the integrand. So we have some similarities and some differences when we solve this one. Switching back to the DotCam. Here we go. To determine the following integral is convergent or divergent. If it's convergent, find its value. Very same principles. We're going to first rewrite this. I noticed there's a vertical asymptote at x equals 2, which makes this an improper integral. Really important to note that. They won't necessarily tell you that. And so from there, we can rewrite this in limit notation. T approaches 2 from the right. Integral from t to 6, 1 over x minus 2 dx. That's our rewrite in limit notation. Then from there, we can keep the limit. T approaches 2t. We take the antiderivative. That would be ln of x minus 2. Evaluated from t to 6. That is our antiderivative. And then from there, we can substitute those limits. T approaches 2 from the right, ln of 6 minus 2 minus ln of t minus 2. Put those in brackets so I know it's all in the limit. Then from there, we can start to evaluate. There's no t's here, so this is just going to evaluate ln of 4. But then if I think about this next part, t's approaching 2 from the right. If I think about this graphically, this would be the natural log curve shifted to the right. And as t approaches -2, I am really, my ln of t minus 2, that's approaching -infinity. So I effectively get ln of 4 plus infinity, which is not a finite number. So that tells me that this integral diverges. As Carla asked earlier, if it diverges, you can't find its sum. So we just say that this integral diverges. With that, I'm going to leave you just 2 examples now for the video this time. And we'll try to cover example 3 if we have time during our Zoom call. See you in a few minutes, and feel free to use this video as a resource if you get stuck with classwork or the exit ticket later on. See you shortly.